Hi, today I will discuss word ladder problem from the Leetcode. Here's the description: given two words, begin and end, and a dictionary's word list, find the length of shortest transformation sequence from beginning to end such that only one character can be changed at a time. Each transformed word must exist in the word list. Okay, and we have here example. We start from this word and we have to go to this word, but we can make only one change at the time. For example, here we can change only one letter. Here this word to O, and we have hot. And then we can change the H, and we have dot, and so on. And we can reach the word this. And we have to also notice that this word isn't here, and we have to check if, I don't know, if we have to check, maybe yes. As I think yes, we have to check if this word is in our word list. Okay, so we have to find a path from this word to this word, and first what is coming to my mind is this is like a graph. This is a node, this is another node, and this graph is these nodes are connected through this one change. For example, from this node and this node is connected because there's only one change I can make and go from this to this. And our solution should find the shortest path in our graph. Yes, and this is our solution, but we can a little bit improve this solution, because to find the shortest path in the graph, the best is brief search. So going from, for example, from this node to all nodes which are connected to this hint. Yeah, so this is yes, this is connected. Lot is connected, and maybe something more or not. I don't know, maybe something more. And then check all this and all these children of this node and children of this node. Okay, and we can make an improvement, and we can go check from both sides, brief search, and waiting if they will meet in the middle or not. For example, we can start searching from this node, and also in the same time starting from this node and go. So from this node we are going here, for example, from this node we are going here, from this node we are going here, and from this node we are going here, and then from this node going here, but we have visited here, so we have a path. For example, I did it right. Hot dot, yes. Dog, yes. Okay. Here, yes, I did it right. So in the end, that, for example, if you have only one search, brief search, on the end this algorithm, there will be a lot of nodes to check. And if we go it from the both sides, we can reduce the time of this algorithm. Okay, and we have to also discuss another thing, how to transform this list to a graph. The simplest will be something like struct with the word, for example hot, and will be a list of words, for example. And in this solution we have to go through this through all these words square. So for this word hot, we can assign it here, and then go dot, I can assign to this list or not, dot I can set, doc I can assign or not, lot, and so on. And for this word we assign here dot, and also we have to go through hot. You check if it's passed here, if this passed here, and so on. This square. Better solution will be to create the hash table, but we make an extra word for a k in this hash table. For example, we will make a map. The k of this map will be our word, but for example hot, but not the exact word, only something is missing here. For example, that will be this star will describe every letter. So and we make a map with and there is, for example, ho star, and this have a list hot, and that's all because it's not more. But for example will be something like OT. This will be list hot and dot. Yes, on even lot. And we will make this map like here. This is a k, and there will be a list of this. And why it's faster? Because we go here, we make odd, and if it does not exist in our hash table, and we add this word in the list. Then we take a dot, maybe come back to the hot. Then we make a h star t, and the same. Then we have the dot, and we will make star ot, and if there exists in the hash table, yes, there exists, we add to the list the dot, and that's all. And it will be much faster. Okay, maybe we will come back to the solution. Here's the solution. This is the main here. This is the main function, and ladder length we have this begin word and end word, and this is the vector of this list of string. On the beginning we check if we can find the end word in the list. I don't need begin word here. This is my mistake. I will change it for the moment. So this is yes, here, and we go here. We go further through the list. If there will be an end word, that is true, and no false. So if there will not find this end word, the return is 0. So here we don't have okay. Then we have to make our dictionary, so our hash table, and I take this list to this function make dictionary. Make dictionary is here, so we have this word list, we have this empty dictionary, the size, because they are all the same size, and we go through this list, and for the our words in this list we make here a small change. For every word we make a small change, so in every word, for every letter in this word we make this new word, which we can push back in the directory. Here we create this here, and then if there exists if this word existed before, we will put to the list that it existed. If not, it will make it a new one, and we push back on the end of the list is our original word, and then we come back to the normal word and so on. Okay, I don't know if we have to come back. Yes, you have to come back, because yes, we are going on the same word. Okay, so we can make our dictionary here. This this will be something like this, yeah. Okay, and the list of this. Okay, so we have made this dictionary. Then we have a queue, because we are going brief search, so in every node we have to remember all this node where we have to go before we check every of this node. So we have to have two queues, because we are going from one side, from this side, and from this side in the same time. Also, we have to make a map with a visited node, and we insert our beginning in the end node. And the same our queue. In the queue we insert the beginning node in the second queue where the queue should start it. And also we remember this int here and this int, the level how many changes we have made. For example, going from this to this, we have made one change, so this will be this level 1. Yes, So on the beginning word, for example, it will be the same word. This will be 1, and here will be and we will make this queue here, and we have checked, so the level was will be 1, so we go only not the same word, I think mean the same only one change. Yes, for example, we find it in this time. Okay, so here we have this while and then our main loop. If our queue isn't empty, we have to go here and here both, because we don't know which queue will reach first. So you have to put here to check every of these two queues. And we have the here result, and we have this function make hop, so make a one jump. We are getting here, putting here this q1 and what we have visited, and the second q what we visited, and the dictionary. If the result is different than -1, then this is the result and this is the end. If they go through this all queues, there will nothing, so there will be 0, because there is not such a sequence. Okay, we can get closer this function make hop. Okay, here. So we have here one queue, the visited, the hash table of the nodes were visited. The second queue have visited this, and the dictionary. So from the beginning we pop from the queue, and we store it in a string s and our level, how deep we are here. And we go through this whole letter in this string, and we save this, and we change only one thing. And then if it is our dictionary, because it can be maybe we don't have this in dictionary, we have to check. We go through this list. For example, we have find this in the dictionary, and then we have this list, and through this read for every word of this find it list, we have to check if we have it in our second visited. If yes, that we have found the path, so we have to summarize our levels. Yes, and that's it. I'm thinking only. I think about can we in the, for example, it will be the same here. Find, and I don't know if it will go okay, if it will be the same word. I think I have to make an extra here at level 1, and here at level also will be 2. because we have here 5, so here 1, 2, 3, 4, and it will be a 5, so they want something like this. There will be 2, even it will be the only one change. And also we have to also extra check if it isn't the same word here. So you may assume that duplicate not here, and no empty and not the same. So we don't have to check it. Okay. So okay, we can go further. So yes, this goes okay. Then so for every word of our list, check if we have found it the previous time, and yes, if yes, this is the end of our solution, and we have to end this. If not visited, we put insert in our visited hash table with level 1 once more, and we put this to the queue to check in the future this word with 1 more level. And yes, on the end we changed this to the previous without the star, and that one -1 in this hop we didn't found our sequence, and the same we make in the second queue, and that's all. And the complexity may be making dictionary here, making dictionary. So we go through our list, so for all words, and we go through our length of our words. So will be multiplexing by n, where n is a length of the I can write it maybe to the end, the place here will be multiplexing by n, where m is size of list of the words, and n is size of your words. Yes, okay. Okay, and we can also discuss about this complexity, and we go through the all maybe here we go here to this queues, and this queues will be in the worst case so big that the size of our list here, and in this function here we go through this all letter in our all words, and here we only make to our queues, so this is this all is the same. So because we are adding here to our queue, and this we are editing our queue, so this will be the same here. The m multiplexing by n, where m is size of the list and n is size of the words. And the space requirement, we can check, for example, the biggest object is here our dictionary, because here we have only the pair of string int, and here we have the string and int also, but here we have string and the list of strings. So it will be, so we have strings, we have the size of the word, because of every letter we have to change, so it will be this and of the words. And the list, for every this we have the the size of the list, so we can make every word in the worst case in our every this string, and every this element of the string consists of n the size of the words. So the space will be n square multiplexing by m. It will be something like this. Okay, thank you for watching, and see you next time. Bye.